Am I audible?
Yes, sir.
Screen is visible now? Screen is visible now?
Yes.
Okay. Good evening, everyone. Let us begin today's session for problem solving session for the course Advanced Power Electronics and Control, which is being taught by Professor Avik Bhattacharya. I am Adnan Farooq Khan, research scholar at IIT Delhi, and I am conducting this problem session on every Tuesday from 7 to 9. Like previous problem solving sessions, in today's problem solving session we'll briefly go through what has been taught in this week, and then subsequently we'll be solving some questions that will help you in your assignments and everything else. So I'll briefly go through what has been taught, give the summary what has been taught in this week. And mostly in this week what was taught about, like PWM rectifiers were taught, also certain power factor correction techniques, and then the discussion moved towards DC-DC converters. And in this week non-isolated DC converters were discussed. And here, like I'll go through the certain things that has been taught regarding this DC-DC converters, and subsequently, like in questions, I'll be talking about this PWM techniques and other power factor correction techniques, because like in question there are some questions related to this power factor correction techniques, and in there we'll discuss in detail about like power factor correction and certain techniques regarding that. And firstly, like I'll be going through this DC-DC converters, some basic concepts related to this DC-DC converters, and we'll be seeing some topologies of the some basic topologies which are widely used everywhere for this DC-DC conversions. So as you can see, coming to the DC non-isolated DC-DC converters. Just a minute. Coming to the DC-DC converters, like three main topologies and basic ones that I'll be discussing is like the buck topology. In buck, what we do, like we have some input voltage is given, and if we want the output voltage that is less than the input voltage, we use this buck converter which does the step down operation. Let us say we have a 100-volt input, and what we want to have is any voltage that is below 100. Let us say we want 50 volts. What we do, we'll use this buck topology for step down operation. And if we want to have a boosting operation, like we are having a given certain voltage and we want output voltage to be higher than the input, at that moment what we use is like boost of a topology. If our requirement is such that at every time we require a voltage that is higher than the input voltage, what we will do, we will use the boost topology at that time. And if we want to have both, like kind of a buck operation as well as the boosting operation, sometimes like the need is we may require voltage which is less than the input, and sometimes we may require a voltage which is higher than the input. At that moment, like only buck converter cannot give us that flexibility to have the buck as well as the boost operation. And similarly the boost converter, in that we don't have the flexibility to have the both kinds of operation. There what we'll be using this topology where I am pointing this cursor, you can see. And this topology is known as buck boost topology. Here what we can achieve at the output is both the at the output what we can achieve is like a voltage which can be lower than the input, or the voltage which can be higher than the input. The idea is same, like that has already been discussed in like first lectures. If we want whatever is here in all the three topology is a switching network. Like during the start of this course what we saw, that if we want to have a certain kind of a voltage at the output, and we can derive that thing from the input. If we do the proper switching, we have a proper switching network, and we will do the switching in a way we can achieve whatever our need to be at the output. Here in the buck converter, the switching is the switching circuit, like you can see here, the switching circuit is such that we can achieve a buck operation at the output. Similar to this boost, we have a switch at the switching circuit in a way that we are able to have the boost operation at the output. And in a similar way, we have a switching network in a way in the buck boost converter, by which we are able to have both buck as well as the boost operation at the output. What we can see here, this in these topologies, typically we have like two devices. You can see like this is a device, or as we can call it a switch. We have a typically two switches or devices in each of these topologies, and what we can see, we have an inductor and a capacitor in these topologies. And if you can see like these switches, these can be both controlled as well as uncontrolled devices we can have for these switches. For these switches, what needs to be there is at least one of the switch should be controlled one, because we need to control that switch in order to achieve a particular goal what we want to have at the output. If we want to have the buck operation, we will switch the device in the buck converter in a way so that we are able to have that kind of average voltage at the output. Similar to the buck in the boost, like one of the in all the three topologies, one of the devices need to be the controlled one, and other can be uncontrolled as well. Like the minimum requirement is one control device. We can have both of the switches with the both of the switches controllable devices. Minimum requirement is at least one of the control device should be there. Also, what needs to be seen here is like in here, if you can see in the buck topology or in every other topology, these devices need to be turned on in a complementary fashion. What that means is, if we turn on one switch, other needs to be turned off at that moment of time. If you won't do that, let us take an example of a buck converter. We are having two devices. If we turn on both the devices, you can see we'll be shorting the source, and that will draw a huge current, and that will like damage our circuitry. And similarly, in a way, if we like uh, uh, switch on both the devices in the boost converter, here we'll be shorting the load, and the capacitor will discharge through this, and the huge current will flow. In a similar way, if both the switches in the buck boost converter are on, what we can see like input voltage and output will get short circuited. So the main thing that needs to be kept in mind for these kind of topologies is like one of the these kind of topologies, what we have to operate these switches in the complementary fashion. When one switch is on, other needs to be off. Besides this, other than these switches, what we have is we have inductor and the capacitor in every other topology. If we take a buck converter, here we can like if we don't have this inductor and the capacitor, this circuitry still will function. Like we will be able to have buck operation, but at the output the voltage would be, in a sense, when we will be turning this on, we'll be getting the voltage at the output, and when this switch will be off, like we'll be getting the zero voltage across the output. So what this inductor and the capacitor does is like it filters out the voltage and the current. But as you can see in the boost converter, we cannot achieve the boost operation without this inductor. Like this inductor needs to be there in one of the interval. When this switch is on, the inductor will store the energy, and when this switch is off and this device is on, then the inductor and this will be connected across the load and transfer the energy to the load. Similar to this in the buck boost topology, this inductor is to be needed, and this capacitor is at the output is to filter out this voltage. And you can see here in like this switching network, and this inductor has been like highlighted with this box. In every other this topologies, you can see there's that in all these topologies, like the location or of these switches has been shifted somehow. Like on the buck converter, the switch is on the input side, and here in the middle, and the inductor is at the output side. And in the boost converter, inductor is on the source side, and if you can see in the buck boost, the inductor is on the middle leg, and the switches are here. Mostly like in the buck converter, this switch is like any of the controllable device like a SCR, thyristor, GTO, IGBT, or maybe a MOSFET, and this can be a diode. And if on this second device is as well a controllable switch, then this is known as the synchronous buck. Similar Now similarly, in the boost, like this switch that is on the mill's middle leg is the controllable device, and this device can be a diode. And if this is an this can be diode, and this can also be a controllable switch like a MOSFET or any other device. And in a similar way, for this buck boost converter, we have this like a controllable switch here and diode here in the anti-parallel batch here with the polarity. I will be discussing this buck boost topology in the subsequent slides, where we'll be seeing this topology in detail. Now coming to this controllable strategies, what we now will see, like we saw different topologies, but we need to see different control strategies for how we will be able to control these DC-DC converters. There are like different control techniques by which we can control these converters, and one such technique is current limit control. This I'll talk about this current limit control later on, and first I'll be talking about other control techniques which are like time ratio control, or which is known as constant frequency control. And what you can see I I'll be talking about this constant frequency control. Here you can see, as the name suggests, like it is a constant frequency. Here we are like the switching frequency is kept constant. As you can see here, let us take a buck converter example. As we know, like if we want to have a certain voltage at the output, like which is lower than the input, we need to switch on the device for a certain amount of a time. Let us say we want to have the we have a 100-volt input and we want 50-volt at the output. At that moment, what we will do, we will switch at the 50% time. However, if we want like higher voltage at the output, let us say 70 or 75, we will be keeping the switch on for the longer period of the time, and T of duration will decrease. However, what we are seeing here, the overall the switching time period is constant. That is what is implied by this constant frequency. In the constant frequency, what happens is, if we want to achieve like different voltage levels at the output, what we change the t on time, and our duty will be equal to t on divided by t on plus t off, like overall time period and the time for which we are turning on the device. If we want to have the higher voltage at the output, will be turning on the device for longer duration of the time. And if we want to have lower uh, voltage at the output, in case of a buck converter, will be appropriately switching the device for a lower amount of time. That is, like we are able to control this device by turning on, we are keeping the frequency constant, only achieving our goal by changing the duty of the switches. Duty, like for the time, or in another way you can say the time for which the device conducts. And coming to the other topology, other control strategy, that is a variable frequency control. Like we saw first, that if we want to achieve different voltages different voltages at the output in case of a buck converter, so what we saw is, like we have to change the duty of this primary device, and we have to, like if we want to achieve the more voltage, we have to switch on the device for the more duration of a time. That means, like we have to increase the duty of the device. One way is that we saw is, like we were able to increase the on time of the device. The other way we can do is, like we'll be keeping the t on time constant, and we will be like decreasing the t off time. This in another way, if you can see, if we are decreasing the t of time, you can see our frequency changes. Here you can see in the constant frequency, like the overall time period of the pulse in the two cases remain the same. That means the one time period is similar in the both cases. But we are able to change the t on time, by which we were able to have different voltages at the output. But in the variable frequency, what we will do, we will keep the t on constant, and what we will play with the t of time. You can see, if my t of time is large, you can see compared to the t on, this t off is large, and you can see we know that duty is equal to t on divided by t on plus t off. Shivanand, can you please like turn off your mic? Shivanand, can you turn on the mic? Can you turn on the mic? Thank you. So here you can see, by increasing the t off, the duty gets decreases, duty decreases, and due to that we'll be having the lower average voltage at the output. But if we want to increase the duty, what we will do, we will change the switching frequency. Like we will be decreasing, leave a switching, changing the switching frequency aside for a time being. What we want to do, we want to have higher duty. We know duty is t on divided by t on plus t off, and when we are able to decrease the t off time, this in other way you can see by this wave, like t on is getting increased compared to the above waveform. However, here you can see that the time period of the waves above and below is not the same. That means like the above wave is having the more time period than below. This means that the frequency, we are changing the frequency to change the duties of this duties, for our converters. So we saw the duties of the converters can be changed in two ways, like in the constant frequency mode, or a time ratio mode, like here we change the time, or time on t on time, or the variable frequency, here we keep the t on time constant, only we play with the overall time period by which we are able to increase or decrease the t of time, which subsequently will increase or decrease our duty of the device. Other thing, like what we see in this DC-DC converters is like the continuous conduction mode and discontinuous conduction mode. You can see continuous conduction mode is like, if this is the current that is flowing, and you see my current is continuous, and in at any moment of time my current doesn't go to zero, like that current doesn't break. If my current is zero, like there is a discontinuity in the current. Here you can see, let us take a buck converter example. As you know, the current through the inductor is have a ripple. You can see the current in the steady state in case of a buck converter has this shape, and you can see the current is continuous in the steady state. However, like if you can see from the peak to from the highest peak of the current to the lowest peak of the current, what we call is the ripple. It is the variation between the top peak of the current to the lowest peak. If you can see, if we can think, if we are able like increase this ripple, and this current will have some average value, and over the average value we have some ripple, and the average will be somewhere here, and we are having some ripple, and here the current is in continuous conduction mode. And now what we will see for the discontinuous conduction mode, when can this current come into discontinuous conduction mode? If somehow this ripple increases, like first it was like getting to this point and coming back to this point, and this was the average value. If somehow this ripple increased and it got up to this value and then came back up to this value, like our ripple is getting increased. If we like decrease the size of the inductor, our ripple will increase. Let us it touch this and here it reaches up to this point, because we have to follow the volt second balance. But you can see there will be one case, if we allow so much ripple, then the ripple will reach to some peak point and its peak will reach to zero. Lower peak will reach to zero. Lower peak will reach to zero. That will be the boundary condition. And you can see if we have this ripple beyond that, what will happen? It will go up to that point and it will reach to a point to zero before this TS from some point. And in case of a buck converter, if we are having an uncontrolled device, second device like a diode, which does not allow the negative current, then this current will be zero for certain time and there is a discontinuity. Like I'll be showing the waveform for that. Is this is what I was talking about. If we'll go up to certain point and come back here and remain, then current will be zero for certain amount of time, then current will again rise, because the device here cannot allow the negative current. But however, if we are having a device that will allow the negative current, then this current can go negative as well. So here you can see one way we are able to have this discontinuous conduction mode in the case of a buck converter. Talking about the buck converter, like if we are able to increase the ripple. The other thing we can see, like there will be some average value of the current here. Let us say this average value decreases. If it comes down, when this average value of the current decreases, it comes to a point here. There will be a point when this lower highest peak and lowest peak will be at this zero line, and that will be the boundary condition. And if our average current decreases after that as well, then our current might go to negative before the time period, like for one switching cycle. So here in the buck converter, like two cases for the discontinuous conduction mode can happen. One is like if we are allow high ripple to go, and then discontinuous conduction mode can happen. Other thing is like if if we have a lower, if we reduce our load and our average current is lower, and in that case we'll be getting a discontinuous conduction mode as well. And similar will be there in other converters depending upon the topologies. You can see when the current can have a discontinuous conduction mode. It is only like we have a device there that is not able to conduct the negative current, that here the current stays zero for that amount of time. I can like show you with this example, like a buck converter. When this current is positive, it flows. When this switch is off and this switch is on, when the current is positive, it will flow in this direction. However, when the current through the inductor gets negative, it has to flow in this direction. But if we are having a diode here, that diode won't allow the negative current to flow. So the current will remain zero for that amount of time. That is this duration. So to have this negative current, we need to have this bidirectional converter. This was about like the conduction modes that can be there in the DC-DC converters. Like they can operate in the continuous conduction mode or a discontinuous conduction mode. Now the other thing is like we want to do a steady state analysis of these devices, these converters. What we have to keep in mind, that we are having like two basic equations of the inductor. LDI by dt is equal to VL, voltage across the inductor, and the current through the capacitor is equal to IC is equal to CdVC by dt. When in the steady state, we are have a periodic waveform of current or voltage. And here what we do is, you can see, if you can take a look at these waveform, that they are repeating after one cycle or after one switching cycle. That means that this wave is periodic, like after one period of one switching cycle, or after every switching cycle, if you take a point, and after this if we come to the same point after one switching cycle, it will have the same value, like that the converter has attained this steady state. And for this, like if the inductor, what we know is, we know this equation for inductor, like VL is equal to LdI by dt. Also, like we can see, write this equation, if we want to have this IL 1 by L integral of, we want to like integrate this voltage, like we'll be getting the current, like we will be knowing this current value and this current value. If we do 1 by L integral of this voltage, we'll be getting peak value of the current, and like IL at the TS instant and IL at the 0 instant. You can see that the value at these instants at 0 and TS value will be the same, like it will be 0. That is, like inductor has whatever energy it will store, it has to give it back, like that is what volt second balance is. Like if this balance isn't there, like if the inductor stores that amount of 10 energy, it doesn't give it back, like there will be a storage of storage, and the current will will be gradually rising up, and will be having an increase in the current, and which can will be reaching a point, like inductor current will increase to a value that it will damage our device or circuit. Similarly, for a capacitor, we have an IC. Here what we do is, 1 by C in IC is equal to VC into this. So we know integral of IC is a charge, and this is known as a charge balance. Whatever amount of the charge that will be stored in the capacitor, and it will give that charge back, and overall, over an average, over a cycle, this will be 0. So we have to keep this in mind. For an inductor, over a average voltage across the inductor is 0, and average current for one period of the capacitor is 0. And these equations are like the fundamental equations that are there to solve these DC-DC converter circuits. Now we'll take a look. We'll be taking a look at this one of the DC-DC converters. Here I'll be like discussing how we do the analysis of DC-DC converter. I'll be talking about one converter, and you can use similar analysis for other for other converters as well, like buck boost, because here like both buck and buck boost operation happens taken up this example. So this is the topology of a buck boost converter, where we have a V input, we are having output, and we have the two switches S1. This is a controllable switch, and here this switch can be either a controllable or it can be uncontrolled, and we have an inductor. And what we'll be doing, firstly, we'll be assigning the polarity. We'll be assigning the polarity to these like the input, inductors, capacitor, across capacitor, and the output. Like if this top for the output, if the top potential is at higher potential is positive and this is negative. We also have like shown the direction of the current. If the current flows in this direction, the current is positive. If the current flows in the opposite direction, the current is negative. We had seen like we can control these devices by changing the duty ratio of the switches, which I had already told, like D is T on divided by TS. If we are like to change the duty of the switch, we change the T on time, TS keeping the time, like T on time will be equal to d into ts, as is evident by this equation. If we want to have if you want to keep the switch for more amount of time, like we'll have to increase like this T on period. This is for the buck boost converter. And you can see, if I turn on this S1, and like I told, like these are in the complementary fashion. When this is on and this will be off, you can see uh, like there are two cases. One is when this switch is on at this moment of time 0 to dts, we will be having a circuitry in this way. We have a Vin and it will charge up this inductor, and we have this C which is across the voltage output. Like the input current will flow across this inductor, charging up the inductor, and we can see that the output current will flow will flow through the capacitor, that will discharge the capacitor. And for this off period of time, we have this waveform. When this switch is off, this switch will be on. For this time, we have a circuit shown in this by this diagram. And coming here, like when I told you, for the 0 to dts time this switch is on, you can see for the 0 to dts period, like voltage across the inductor will be equal to V in, VL will be equal to V in, you can see here. And you can see at the output side, like we have two currents, IC and I out. If we apply like Kirchhoff's current law here at this node, the sum of these two currents will be equal to 0, and that will give, that is IC plus I out will be equal to 0, that will be IC will be equal to minus I out. What it shows, like the convention that we had taken up here, that the current flowing in this direction is positive, is wrong. Like it will be, the current will be flowing in this direction. Also here in this, here what we can see is, here the current that is flowing through the IC is the negative of the I out, that will be in this direction. Sorry, got it? And the voltage across the inductor will be equal to VL will be equal to V in. Now coming to the off duration, that will be from dts to ts here, as I had shown earlier. In this you can see, like voltage across the VL will be equal to V out. Got it? That this voltage across the VL will be equal to V out, that this voltage will come across this. And you can see, applying the Kirchhoff's current law to these nodes, IC, some of these currents will be equal to 0, and you can see IC will be equal to minus IL minus I out. Like the current here flowing here will be something like here. These were the equations, like we were able to get these equations for two modes, like for the turn on mode when this switch is on, for one mode when this switch is on. Now what we will do, now you saw, like we got, what will we do, like we have like two equations, fundamental equations. You saw that one equation will be for the voltage across the inductor, and one will be the current across the capacitor. That is why we were interested in to find the voltage and currents across in different time durations across the inductor and the capacitor. Like applying this, like for 0 to ts VL dt, we know like it will, VL is equal to V in for dts time, and VL is equal to V out for 1 minus dts time. That is one equation. And if we solve this, you can see our gain or transformation ratio, like V out will be equal to minus D divided by 1 minus D divided by V. What this means, like we take a D can only have a positive value. Like if you give some value here, D, let us say 0.5, you can see, or 0.4, you can see when this V in is positive, V out will be negative here as per this equation. What this means, like if you can see, sorry, like just a minute. if you can see, we had taken the assumption like positive here and negative here. By the equation, that what it shows is like actually this is not the assumption is like we have to take like positive terminal will be here when their input is here, we'll get a voltage at the output which will have a positive here and negative here. Got it? That is one thing that we got from one equation by applying volt second balance across this inductor. Now what we'll be doing, we'll be applying charge balance across this capacitor. We know that for one time period, time interval, we know IC is equal to minus I out in when this switch is on, and equal to minus IL minus I out when this switch is off and this switch is on. Similar way, you saw that IL will be equal to minus 1 divided by 1 minus D into I out. You can see that what this means, like the current will direction flow will not be in this direction, it will be in the opposite direction. This is like how you can this was for this solving this circuitry with these equations. Like you took certain assumptions like this will be the here I have done the notation like positive terminal will be here, negative terminal will be here. But here what we got from the equations, like what assumptions we had take is wrong, and actually that current direction will be here and output voltage plus will be here and minus will be here. Like this was the one way, like you saw how to solve this circuitry. This was the one of the topology like buck boost converter. You can do similar analysis for other topologies like buck and boost converter. Like here we have what we'll do when you can see this is the this will be VL across the inductor. You can see when this switch will be on, VL will have V in minus V out for the DTS time. For 1 minus DT, this switch will be on, off, this will be on, that this VL will be equal to V out for the buck converter. Similarly, you can do for the you can see you can take the direction of the current certain way, and you can apply, then you can apply that volt second balance to the inductor, then charge balance across the capacitor here, and you can come from where we derive that equation. Like for the buck converter, we have V out by V in is equal to D, and similar concept like this is how we solve these circuits or converters, applying these equations like volt second balance across the inductor and charge balance across the capacitor, and we come up with different equations. And in a similar fashion, you can do the analysis of the other converters as well, like buck, boost, and different topologies. This was like what was taught in this week, and now what we'll be doing is we'll be moving towards the problem solving, yeah, to these concepts, regarding these concepts. Like here is the first problem. You can see the first problem is the average value of the output voltage of the non-isolated DC-DC converter is controlled by current limit control. And I had told you earlier, like I'll be talking about this current limit control later on. Here I'll be talking in detail about what is this current limit control. This control is only possible in which type of load? Like we have different options here, like inductive, capacitive, resistive, either inductive or capacitive. Got it? I won't ask you to like answer what will be the answer to this question. First I'll be telling you about this current limit control. Like some of you have answered the question, and I think this is the correct answer, but I'll be going into the detail like how this is the correct answer, and we'll see. We'll be discussing about this current limit control. You can see, let us take this circuit. We have a switch like a buck converter cell without the inductor. We have a load that is inductive, we have a resistive, and this I told you like like for this we have be having the waveform in a way like when we have an inductor, when this switch is on, you know that this voltage will reverse bias this diode, and this voltage will come across this inductor. Got it? When this voltage will come across this inductor, we know like the current through the inductor cannot change instantaneously. Like from the equation, L is called L di by dt, because if the current will change instantly, like we'll be having a very high voltage, which is not possible. Or if you are able to like break the current, like we will get such a huge voltage spike, like that can damage our system. So from that equation we know like the rise in the current will be gradual. So we know when we turn on this switch, the current through this will rise to some point. So here what I will first tell, like for this current limit control, what we will do, we will first like define a band. We will be defining a band that will have a maximum value and a minimum value. And let us say that the point the maximum point to which the current can go is I max, and the minimum current that it can go is I minimum. Like firstly we defined a band, like this is the band, this is my band. So now what we will, when we will switch on this device, the current will gradually rise and it will hit the upper band, where upper band I is called I max. And we write our logic in such a way that when this current hits the upper band, the switch turns off. This switch turns off. You got it? The current is gradually rising, and when it hits the upper band, the switch turns off. And what it does, when this switch is turned off, then this the current in through the inductor cannot, like we have been talking about this throughout these some of these sessions, like it cannot be broken instantaneously, like it will then flow through this diode. So the current through this will decrease, and then after a certain period of time it will reach the lower band, and when it touches the lower band, and we'll be writing our logic in such a way, like when it touches this lower band we will be telling the switch to turn on. When it touches this lower band, this switch turns on, and again when this switch turns on, we'll be getting some positive voltage across this inductor, and the current increases. In a similar fashion it will be a steady state operation, like current will increase because L is constant, this slope will be constant, L di by dt will be constant, like this voltage is constant. And when this slope is rising, it will hit this peak value, switch will turn off, then it will decrease, it will hit the lower value, and here the switch will turn again on, and this will go on in a similar fashion. This is the current limit control. This is how we do the current limit control. Now we'll see, can this current limit control be done in case this was the for the inductive load. You saw like we will be able to do the current limit control in case of an inductive load. Now we will be seeing if we could do this for a resistive load. Now let us say this is our circuit. You know, for a resistive load, like when this S is turned on, this voltage will come across this resistor, and the amount of current that will flow will be equal to V in by R. That will be some constant current here. So if we have defined the band here I max to I min, but our current flows through that band, but it will be on a certain portion of time. It will be a constant current. Here I have shown like the switch, if we switch off the if we turn on the switch after a certain amount of time, after a time dts, then this voltage will be at the output will be 0, and the current will also be 0, because like we don't have any inductance or so, like current will go to the peak value and come to 0 and when the switch will be turned on. And if we don't have this logic, and if we have turned the switch on and have this current limit control, the current will be constant through the band and it won't be touching this upper limit and the lower limit. So our switch will be on for whole period of the time. It won't like turn off, on and turn off. This means that in this current in the resistive load, this current limit control is not possible. You got that point? In a similar fashion, you can see if we have a capacitor here, we know that through the, like we said about the inductor, the current cannot rise instantaneously, but through the capacitor current can rise instantaneously, but the voltage cannot rise instantaneously. If we have a capacitor, like when we apply this voltage, and maybe capacitor will be in the discharged mode and it will draw a huge amount of current, and we'll be getting a spike of current to a higher value at the start and then the current will come down. So what will happen, that switch will turn on here when it will touch that this upper band limit, then this device will turn off at the starting instant only. So in case of the capacitor also, you can see for the capacitors this current limit control is not possible, as well as it will give a like false triggering of this switch. If at any moment like current shoots up, like it won't, our objective won't be met, like for what amount of time we want to have this device on and off. So the correct option to the question to the question 1 is inductive. Coming to the next question, which of the following techniques help to improve the power factor? Like there are some factor improvement techniques given here. Like there are certain techniques like extinction angle control, symmetric angle control, pulse width modulation control, and all of the above. Here also, like I won't be telling you to give the answer to here, because like we'll be discussing in detail this power factor correction here, and all will be going through all these control techniques like extinction angle control, symmetrical angle control, and pulse width modulation control, and we'll be seeing will they improve the power factor or not. Firstly, like we will see a simple, like a normal operation of like a full bridge thyristor based like AC/DC converter, like which we also saw in previous session. We know like these SCRs, we are able to control the turn on time. And here you can see the load is a constant current. We know that load is highly inductive, therefore this constant current. So here you can see like this is the input, like gray is shown by the input, gray portion is shown by the input. So you can see here like at the alpha moment, like we are turning the devices on, like diagonal devices are turned on, this and this, and when the alpha position is reached, like these devices are turned on, and it will, the current will flow, and at the output we'll be getting this voltage. When the pi this hits, had there been no freewheeling diode, the current would still have flown up to this point and we'll be getting this negative portion in the voltage as well, like we saw in the previous problem solving session in some of the problems. So due to this freewheeling diode, the current will flow through the freewheeling diode and we'll be having the zero voltage in this duration. And after that, in a similar fashion, like these two devices will be turned on and we'll be having the output voltage like this, and it will follow the same thing will follow here, like we'll be having a zero portion, then we'll be having this. This was about the output voltage. And what about the input current? We know that when these two devices are on, like we'll be having the positive, when this will conduct, like the positive current will flow, and when these two devices will be on, like the source current will be negative. Got it? Also, like you saw, this blue color will show us our source current. This is a quasi square wave. which we saw also in the previous problem solving session. And if we do the Fourier analysis of this Cauchy square wave, it will have a fundamental and subsequent other harmonics. Also, what we saw in the previously what we saw, that the zero crossing of this will be alpha by 2, like here. So the zero crossing of the fundamental of this Cauchy square wave will be alpha by 2, alpha by 2. And if you can see, our source starts from 0, that means there will be some alpha between, like this fundamental of the source current will lag the fundamental voltage by some angle alpha by 2. And the more our alpha is, like, we'll be having the more angle, displacement angle between this fundamental here and fundamental of the voltage and the fundamental of the source current. You got it? And like, displacement factor is the cos of this angle, and we have this power factor, like fundamental RMS by overall RMS into cos phi of this angle. And if we'll be increasing this alpha, and this cos phi will be decreasing, that means our power factor will be getting deteriorated. Now we will see for the different, like, control techniques. This was for the normal case. Now we will go for this first, like, extinction angle control. What happens in this extinction angle control, what we do, instead of the turn on interval, what we control is the turn off time. Like we saw in the for SER, we turned on at a certain angle alpha, and we let it, and these were SER. When it reached, like, the pi interval, after that like, they were itself, like, turned off due to the circuitry. Here, like, we have to turn off these devices, so we need a device in such a device which are having, like, which we can turn off, which we can have a control turn off. Like, SCR cannot be implemented here, as they only have a control turn on. So here we'll be using the GTOs, which will be having like a turn off control as well. So here, in a similar fashion, like, they are here these devices are turned on at the 0 instant, and after reaching a certain angle beta, they are turned off. And after that, like, the load current will freewheel through the freewheeling diode, and load voltage will be equal to 0. After that, at the 0 interval, these two devices will be turned on, and after they reach a certain beta angle, they will be turned off. We saw that when these two devices are on, like, the source current will be positive, and when these two devices will be on, source current will be negative. And see, here also you can see, we are having a Cauchy square wave that will have a fundamental and other harmonic components. But here what you can see, compared to the previous, that the current was lagging the voltage by some angle. Here you can see, due to this turn of control, like, this current is leading the voltage by some angle. This angle, like beta by 2, you can see that this portion will repeat here. Repeat now, like, if you can see this portion, this will start from here, the current is here. That this means, like, if we are having an extinction angle control, like, we'll be having a leading power factor. When this is happening, leading power factor, we can see most of our loads are like lagging loads. We'll be having the inductive loads or something loads, and they'll be drawing some reactive power from this grid. And if we'll be able to have this circuit in our system in somewhere which is able to have the leading power factor, it can compensate for the lagging power factor for some other converter. Like some converter is drawing some lagging power factor, this will be this will be having the leading power factor, it will be like giving the reactive power to the grid, so the overall will be compensated. This means like if we are having some circuitry with the extinction angle control connected to our system, it will provide a leading power factor and which will compensate for the lagging power factor of the other uh, other converters. So with thus, like you saw here, with the extinction angle control, you are able to improve, we will be able to improve the power factor. Coming, just a minute. Now coming to the second thing, that is the symmetrical angle control. Symmetrical angle control is like we'll be turning on at some in, we'll be using a device which are controllable, where we'll be able to control the turn on as well as the turn off, and the angle where we will turn on will be the similar to the angle where we will turn it off. Let us say here, let us say we are turning these two devices at an angle alpha, then this the output voltage will follow this wave like in this position, and at some angle beta it will turn off. Like this whole conduction period is beta, at this instant we are turning off this angle. Like you saw, when we are having this delay of a certain angle, what we got is like a delay, what we were having is lagging power factor, but that some angle, like this current was lagging the voltage by some angle. And when we did this extinction angle control at the out towards the extinction, what we saw is like our here in the previous slide, like our current was leading the voltage by some angle, beta by 2. Now you can see here, if both of these angles are same, then one would compensate for the other, and we'll be getting the voltage and current having like common or the same 0 point pi and something. This will mean like they will be having at a unity power factor, or like cos angle, displacement angle between them will be 0, or the power factor will be cos phi, like that will be 1, displacement factor will be 1, that's the maximum that will be possible. So how will we be doing this? Like for this, how will be doing the switching? Like we'll be having a triangular carrier or something. Here you can see this kind of a wave, and we'll be having some modulating signal. Let us say this straight line you can see. So our logic will be in such a way, when this modulation signal is higher than the carrier, like this triangular, will be turning on these two devices. So when this modulation here, you can see our triangular wave is higher, so our switches are off. At this moment of time, our modulation wave is higher than the triangular wave, so these two switches will turn on. When this turns on at this moment of time, our triangular amplitude will be higher, so this will be turned off at this instant. Since this triangular wave is symmetric, therefore we'll be having a symmetric, this angle will be symmetric here and here. We'll be able to have these like turn on angle and turn off angle same, and because of that we'll be like one would compensate for other, and we'll be having an improved power factor. This was other thing, other control topology. Now we saw like because of the extinction angle control, we are able to have a leading power factor, and which was if we have that in certain circuitry, we will be able to compensate for some lagging power factor, and therefore if we because of that topology, because of that control scheme, or with that topology, we'll be able to improve our power factor. And now we saw with the symmetrical angle control, we'll be able to improve our power factor, because one angle will compensate one for other. Therefore we'll be having a voltage and current in unison. Now we'll move to other control technique, that is pulse width modulating control. Here what you can see is like the device in this previous what we saw, we had like the carrier which was having the frequency double that of the fundamental. You can see like the fundamental, if we have is 50 hertz, that this is the double, like in a half wave, in the half cycle we are having the one cycle of this triangle, one triangle in this, that it was having the frequency, carrier is having the frequency double that of this. Now in pulse width modulation, what we do, we'll be having the carrier with the higher frequencies. Here, like for the sake of showing what happens, is like we have showing 1 2 3 8, like the carrier frequency is 8 times the fundamental, the this modulating signal. And what we do is we have a modulation signal here, you can see a straight line, and the logic here is similar to the previous. Like if our modulating signal is higher than this triangular, the switch will turn on. You can see when this is higher, this will turn on, like these two will turn on, it will start conducting, and when this is higher, that it will turn off, and we are having the output voltage to be 0. And when this instant, this will turn on and this will turn off, this will turn on and this will turn off, these two switches. And for the negative period, like it will happen in a similar fashion for these two switches, for the other diagonal switches, for other two diagonal switches. We know like the current, when these two switches will be conducting, the current will flow, the positive current will flow, and when these switches will be off, current will freewheel through the diode and it will be 0. So instead of a, like here what we were achieving a Cauchy squares waveform for the current, here we are having a pulsed current waveform through the source here, here. And in the negative cycle, like these two devices will be on, these two diagonal devices will be on, we'll be having a pulsed current in the negative half. If you will do the Fourier analysis, you can see, since like this is the constant, that initial angle and final angle is same, the fundamental of the voltage and the current will be like somewhat very near, or if there will be some variation between them, uh, it won't be as much as the starting with this alpha. Also, if you can do the Fourier analysis of this current, you can see like this fundamental will be very close to this, the fundamental of this voltage, you can see. Also you can see this, it will have this, if you can see like do the Fourier analysis of this pulsed source current, you can see that we'll be having the harmonics that we have in this, the value of these harmonics will be somewhat reduced compared to the previous Cauchy square wave. This is all mathematical, you will go through, do the mathematical analysis of these two waves, and you will see this thing. Now now there is other thing. Now here what we have, we were having a modulation signal that was very constant, that was a constant like this. Now if we have a modulation signal that is sinusoidal, so instead of having a constant modulation signal, we will be varying our just a minute, we will be varying our modulating signal in a sinusoidal fashion. So having the same logic as previous, like when the modulation signal will be higher, our switch will turn on, and when the triangular will be higher, it will turn off. So you can see like this positive wave, it will turn on here, and then the here, like for initially it will be for the smaller duration, then the duration will gradually increase, and then it will decrease. Here like I have seen shown this carrier having like 8 times the frequency, which is very low. Actually it is like 20-40 times. And in a similar fashion, when you know like this this conducts like our switching current will source current will be positive here, and it will be a pulsate waveform like this. And you can see, because of this sinusoidal pulse width modulation, if we average, it will be more closer to the sinusoid compared to the other topologies previous other topologies previous other topologies. If you can see, like do the average of one this high frequency like wave, that at the beginning, since it is this high frequency is for the lower duration, average value will be lower, and subsequently this increases, overall value increases, and average value will gradually increase, and it will reach to a peak value, then it will subsequently decrease. And you can see like because of this pulse width sinusoidally pulse width modulation, the current that will flow through this source will be closer to the sine wave, and it will be having the lower harmonics compared to other. And besides this, the power factor will increase because the wave is more closer to the sine wave compared to the previous topologies. The power factor improvement in this will be very high compared to the other topologies. There also power factor increase, but compared to that, here the power factor increases very much. So this is the here you saw that the power factor is improved because like our source current is sinusoidal, and similar to our source voltage. So we saw like these different control strategies like extinction angle control, and it was able to improve our power factor by providing the leading power factor, which was able to compensate for some lagging power factor, and we can improve our power factor by this as well. From symmetrical angle, you were able to see that it was able to compensate for the starting angle like alpha with the beta, and overall we were having an improved power factor. Like with the pulse width modulation, you saw how like the source current was more closer to the sine wave, harmonics got reduced, as well as like it was having a symmetry at the input at the output, and we will be having like power factor also got THD and power factor got improved in this pulse width modulation control as well. So here the answer is all of the above. So here with this question, I think we'll be taking a break for like 5 minutes, and we'll come and move forward with the question. Like if some of you there can try this question in the meanwhile, and you can see the answer, and we'll be discussing the answer to this question. Like we'll be joining back at 8:20. Is that fine? Am I audible? Okay. Okay, continuing, like now will be more towards like question number 3. The question is like, in case of a multi-pulse width modulation method, if the amplitude of the reference wave and the carrier wave are made equal, then the pulse width in the decrease is A is 90, 100, 0 and 180. Like, can any one of you answer this? Then we'll see what is the current option for this. Anyone there? Like, some of you are saying C. Any other can try? So we'll go for this, like we'll see for this question. You know, what we are told here is like, in case of if the amplitude of the reference wave and the carrier wave are made equal, like like this is the carrier wave, this is our modulating wave, this is the peak amplitude of the carrier wave, and this will be our amplitude of this is the amplitude of the modulating wave. We know that for our switching we have our logic in such a way that when this modulating wave is higher, like we turn on our switch, and when this is lower than this triangular wave, that will be turning off our switch. If we are having, like, now let us consider the first case. Like, now we can have a logic in other way around as well. like when this modulating wave is lower, then it is the logic is all up to us. If we are having a logic, then when this modulating wave is lower than this triangular wave, will be turning on the switch. You got it? Now coming to the first, like now what we'll be doing is, like when this will be equal, like the amplitude of the modulating wave will be equal to this, the peak of the triangular wave. Now, and our logic is such that when this modulating wave is greater than this triangular wave, so you can see at that moment of time our MA reference will be greater than this carrier for the whole duration of the time. If we move this upwards, when this amplitude will be equal to this, our switch will be on for the whole duration of time. If you take an interval like for 0 to pi, for 0 to 180 degree, you can see that our switch will be on for the whole duration of the time for 0 to 180 degree. When our reference is greater than carrier, logic is such a way that reference is greater than carrier. In that case, the answer will be 180 degree. Now, and if our logic is such that we have this modulating wave, when this carrier is greater than this modulating wave, our switch will turn on. But when this will be same, you will see that that won't happen at that moment of time. Our switch won't turn on, like that will be for the 0 degree. So here, like this question actually has been framed for the previous year course that was taught for this advanced power electronics, and mostly they implemented this logic. When the carrier is greater than this reference, like then only turn on, the switching was happening. And if we take into that or what is being taught in the course, then the 0 degree is correct answer. Now moving towards the fourth question. The variable frequency system control of a chopper is also known as, like this is a straightforward question. I think everyone should be able to do that. And if you could try, like what will be the correct option to this question? Anyone? Like I think this is the first thing that I discussed in today's lecture. This simple as is implemented by this, I like the variable frequency system. Here only it is telling the answer to this question, like it is the variable frequency. So here the option B is correct to this question, like the frequency modulation scheme. Because in the pulse width modulation, what we do is we have the constant frequency, uh, and we change, like turn on and turn off time is changed. And here by changing the modulation amplitude, if we move modulation amplitude higher, like our turn on time will be higher depending upon the logic we have used. And hysteresis in control you can also achieve, like pulse like variable frequency option, but that hasn't, we haven't like uh, read that. Like here the correct option is frequency modulation scheme. Coming to the fifth question, a single phase full converter is made to deliver a constant load current. Yeah, here we, like this is related to what is being taught previously. Here we have is giving a single phase full converter, and we have the constant load. And what is giving, like the for the zero firing angle, like at the zero instant the switches are being turned on, the overlap angle is around 15 degrees. We know when this overlap angle is given, that means in the circuit there is some source inductance which is causing this overlap. What we have to calculate is calculate the overlap angle when the firing angle is 60 degrees. So overlap angle for the 15 degrees of a 15 degrees is given for the firing angle of 0, we have to see what will be the firing overlap angle for the firing angle of 60°, and there are certain options. We will see what is the correct option amongst them. Just as I told you, like this is the circuit of the single phase full wave converter, and you can see, we know that the source current is sort of will be a square wave here, and you know that not a and because of this source inductance, the transition from the negative to the positive current, from the negative to positive, won't be instantaneously. It will have some delay because of this source inductance, and that interval is given by this mu, that is the overlap. That will be the overlap where both of these devices will be on when it will be transferred from this device to the device. So like, and we know that this current will be lagging the voltage by some angle alpha. We have already seen them, but here it will be lagging by alpha plus mu by 2. That mu is this overlap angle. So, and also what we know here is, we know this equation for a single phase converter that has already been taught and derived in the course by the sir. So here you can see we have like cos alpha plus mu is equal to cos alpha minus twice omega ls I naught and vs. You know, like in this question, like the only parameter that is being changed is alpha and mu, and we know that the source inductor will be constant here. All nothing is talked about this current and voltage source. What we will assume that all these parameters are constant, and the only variables are this alpha, and what will vary is mu. Now what we'll be having two cases. The first case is what is given to us, like alpha is 0 and an overlap angle is 15°. Got it? So when this is given, like both of these parameters are given, we will be able to calculate this thing, what it will be equal to. And putting these values here, like alpha equal to 0° and mu equal to 15°, we'll be getting the value of twice omega ls by root 2 vs I naught will be equal to this much amount. And we know, like since these parameters are constant and this will be constant, since these being the constant, we know now that the value of this component is equal to like 0.034. Now this is known to us also. Now we will be moving towards the second case. We know that this constant will this quantity will remain constant. For second case, what we are given is alpha. Now alpha is given to us is like 60°, and we won't be knowing this mu part. This mu is to be calculated. Now we know this is known to us, this will be constant and have the value, this value 0.034. now this is known to us, this is known to us, and the only value that is unknown to us is mu. And if we solve this equation, mu will be coming out to be 2.22 degrees. Therefore our first option is correct. Now coming to the sixth question. The question is, in a single phase semi converter with a resistive load, a firing angle alpha degree. Firing angle is alpha, like our devices are turned on at an alpha degree. Each SCR and freewheeling diode would conduct for. I think like this is a good question which every one of you should be able to do, because like we have discussed this topology in detail. I'll give you some time, like maybe you can ask, you can like give answer to this question. Like, can anyone tell like what will be the answer to this question? And read the question carefully. Anyone there? Someone has answered. Maybe any other can tell. Anyone else there? There are like 8-9 students. Everyone, like, there are different. Someone is saying, some are saying B, some are saying D. Like, let us see. Here the tricky part is, like, you have to look for is what is given here is it is an resistive load. That is the tricky part. And like, we have a single phase semi converter. In semi converters, we have read that like two of the devices will be controllable devices and two of the devices will be uncontrolled. This can have that one leg, top two device can be controlled and bottom two can be uncontrolled, or one leg can be controlled and one leg can be uncontrolled. And we know that this freewheeling diode won't be conducting for the resistive load. As soon as this voltage will coming out to be zero, current will also come out to be zero. And this freewheeling diode only takes part when there is an inductive load, because it has this current is to be flown through this freewheeling diode only because of that inductor. Because like we cannot interrupt the current through the inductor instantaneously. And that was the tricky part. Like, you got that because of this resistive load, this freewheeling diode won't conduct at all. At least the conduction period of this freewheeling diode will be zero. Now we have to see for how much time these thyristors will conduct. You can see at alpha duration the switches are turned on, and when this voltage will come try to become negative, this will be zero. The current will be zero, because like after a certain alpha time the pulses to the other switch, and the diode will other switch will be given, and the diode with that switch will start conducting, and the output voltage will be that. And you can see from alpha to pi, like first T1 and D1 will conduct, and then for the second half T2 and D2 will conduct in from this alpha plus pi. So if you can see, taking this one half cycle, that this thyristor or devices will conduct for a period like from alpha to pi, or in other sense you can say pi minus alpha. Like this duration will be equal to pi minus alpha. Therefore, uh, the answer to this question is like D. The SCR will conduct for pi minus alpha degree, and freewheeling diode wouldn't be conducting at all because the load is resistive. Had there been an inductive load, then this freewheeling diode would have started conducting for that alpha period. Now coming to the seventh question. In a three-phase, three-pulse M3 type controlled converter, T1 starts to conduct at 30 degree plus n degrees, like the alpha 30 plus some alpha n. At what angles do T2 and T3 start to conduct? Assume that the conduction sequence is T1, T2 and T3. So here what is given is we have an M3 type of a controlled converter. This means only we are having like a three devices. That means like in a three phase we are having only three devices. Therefore, like this is a half wave converter. You can say that is a three phase half wave converter. And now we'll see the waveforms of this half wave converter, and this coming to the solution of this. You can see like these we are having the three phases, and we are having the three devices T1, T2 and T3. And we had already seen for this natural commutation, like you can see these devices are with the common cathode configuration, and the device with the highest voltage at any instant will be conducting. So let us say like this at this moment, this will be the point of at this 30 degree will be the point of natural commutation for like T1, and at 150 degree point of natural commutation will be for T2, and to 70 degree it will be for T3. You can see here, like, but our devices are being turned on after an instant, let us say alpha. Here in the question it is given n degree, you can assume like n is equal to alpha, it will be turned after a certain instant. So here you can see, like, after our T1 will start conducting with 30 degree plus alpha degrees, and it will conduct to a point. Here at 150 degree would have been the point of natural commutation for T2 had it been like triggered at that moment only, but because in HCR it will be triggered at an plus alpha degree, so the point of conduction will be from 150 degree plus alpha, and similar will be for this, for the third T3 it will be from 270 degree plus alpha. So you can see the answer to this question will be like B, 150 degree plus n degrees and 270 degree plus n degree. That is the answer to this question. Now, like, coming to the question 8, it is given like, in case of a constant frequency system, T on is equal to 1 by 4 of T. If the chopping frequency is 2 kilohertz, find the value of T off. What is given here? T on is given, frequency is given, that means from the frequency we would be able to calculate the switching time period, Ts, and we know like T on will be equal to T on is T on divided by T on plus T off will be equal to D. So you should be able to, like, you can try to solve this question and can see and can say that which of these options is correct. Anyone? I can like give you 1-2 minutes like to solve. If anyone is interested in solving this question, you can try to solve this question, or then after a minute or so we will move forward. Anyone has solved this question? Like, this is a simple mathematics involving the basic equations that we saw at the start. No one with the answer? No one? Oh, someone has solved it as D. At least someone has tried. So let us see if this answer is correct or not. So what was given to us, like, we know T on was given to us, and we know that also what was given to us is the switching time. From that we can get the overall time, and from that we can get the T off time basically. So the total time period will be given by 1 divided by Fs, that is 1 by 2000th of a second. Also what was given in the question is like the T on duration is 1/4 of the total time duration, that is T by 4. That is, that if you do 1 by 4th of this 1 by 2000, like we will be getting 1 by 8000, like this is the T on time. And what we had to calculate is the T off time, and if you like substitute these value in the first equation, you can get like T off will be like 3 by 4th of this T, and you can see that it is a 3 by 8000th of a second, that is 3 by 8th of millisecond. Therefore the B option is correct for this. Now coming to the 9th question, in the current limit control method, the chopper is switched off when? I think everyone should be able to answer this question, like we discussed it in detail in the first question. In the current limit control method, the chopper is switched off when first option is when the load current reaches the lower limit. Second option is when the load current reaches the upper limit. Third option is load current falls to zero. And last option is none of the above. Anyone can answer this question. One of the students has op, and there is a second option, and I think most of the students are like answering the B. Let us see what is the correct option. So we have seen that for the current limit control we define a band. In the current limit control, like we defined a band with the peak current and the lowest value of the current. So we had seen like at an instant when the current reaches the peak value, will be switching off the device, like the switch at that time. And when this current will be reaching the lowest value, then we'll be turning on the device back. So here you can see when at the start the current is at the zero, touches the lowest value, we are turning on the device, and the device and our current starts rising because of the inductive load. The current will gradually start to rise. When the current gradually starts rising and when it touches this peak value, at the up to that this point, like when the current touches the peak value, the switch is on. As soon as this current touches the peak value, the switch turns off. This means that we'll be turning off our device when the current reaches the peak value. That means at the peak value the current switch will be turned off. And when this current reaches the lowest value like of the band, at that moment we'll be turning on the device as again. This means like we turn off the device at the peak value and turn on the device at the lowest value. So for the what our question had asked, like when the device's chopper is turned off, this means like the load current reaches the upper limit. At that moment uh, we turn off this switch or device. That was a question number 9. Now I'll be going to the last question, that is question number 10. And here it is given, we are having a step up chopper that has an input voltage of 220 volts and an output voltage of 660 volt. A step up chopper is nothing but a boost converter. Like we call it a chopper because of a thyristor, that is switch is a thyristor. We have a step up chopper, or you can say a boost converter, where input voltage is given, that is 220 volts, and the output voltage is 660 volts. Also what is given, if the conducting time of the thyristor chopper is 100 microsecond, then what will be the pulse width of the output voltage? This means that T on time is given. This is the conducting time, is the time for which like this thyristor will be turned on, that is also given, that is 100 microsecond. And what we have to see, then what will be the pulse width of the output voltage? We have to see the output of this output voltage. What will be the pulse width of the output voltage? So we'll be going through the, you can see we are having a step up chopper has this configuration, like boost converter has the two devices. This will be the controlled device, like I had already told, and this will be the uncontrolled one. So when this device will be turned on, we will be having this configuration. At that moment what will be doing, like that inductor will be connected across this input. So the voltage across this inductor will be storing the energy in this interval. Now the other interval, when we'll be switching off this device, then you can see, because this inductor current cannot be broken, it has to continuously conduct. That will forward bias this diode, and it will during the t of time, this will be the circuit. So we have now, for the t on time, this is the circuit, and t off time we are having this circuit. So also what is given here, we know for this step up chopper, we have the equation derived by using, like, if you can do that steady state equations, like voltage across this is 0 and average voltage across this inductor is 0. So what we come out to be equation, this V out will be V in divided by 1 minus D. Also you know that D, we know that is the duty, it is the duration for the time D. What we, how we define the D is T on, the duration for which our device is turned on, divided by the whole time. T, that T will be equal to T on plus T off. This is the whole time. Also, like, we can get, using the equation first, we can get the value of t, that will be equal to d will be equal to 1 minus, if we can rearrange this equation, equation 1, you can see that d will be equal to 1 minus v in by v out. Correct up to this point? So when d is given, like d is not given to us, like we are only given like this, v in and v out is given to us, so we can calculate the value of d, that will be equal to 1 minus 220, that is the input voltage that is given, divided by 660 volts, that is the output. So if you solve this, our d comes out to be equal to 2 by 3. So what we had to calculate, then what will be the pulse width of the output voltage? So here you can see what we had to calculate is, if you go through the circuitry, we have this at the turn on time, the voltage will be across this inductor, it is charging up this inductor, and the output is disconnected. So this, when this output is disconnected, we won't be having any voltage across at the output at that moment of the time, because we don't have any capacitor that will hold any voltage for like continuous amount of time, since like we are having a diode and then load. During this t on time, there will be no voltage. Got it? Now when we are turning off this device, as I already told, it will turn on this diode. What would happen, that this voltage will come across this V out, V input. When this comes out V across voltage, that means like the output voltage will be there for the t off interval of the time. That is, so what will be the pulse width of the output voltage? So the width of the output voltage will be equal to the t off time. So if we are able to somehow calculate this t off time, we will be able to calculate the duration for of the output voltage. So that is what will we do now. So we had input, we had the output. What we did first, we calculated the d. Now d is known to us. Got it? Also this t is known to us, that is 100 microseconds. So now we know that t off will be equal to t minus t on. Got it? Now also we can, sorry, like t on is given to us, like for duration for which the device will be turned on, that is given to us, not the t. So this is not known to us, like, but we can represent this t in terms of t on and d, like by this equation, like t will be equal to t on by d. Here we are able to calculate the value of the d. If we substitute that, like t off will be equal to t minus t on, that this t will be equal to t on by d minus t on. Now what we got is, we got everything to calculate this T off we got like in terms of T on what is known to us and D what is already known to us. So when we substitute the value of T on, D and T on, what will give the value of this will be equal to like 50 microseconds. That is answer to this question, like 50 microseconds. And is this answer understood this question? That is what was given to us. We were given V in and V out, also the conducting time of the thyristor, that is T on, not the T, sorry for that. T on time was given, and then what will be the pulsative voltage of the output voltage. We had to calculate the output voltage, and what we were able to see is that the output voltage waveform will be there only during the T off time, because during the T on time output voltage will be having this interval where the output voltage will be cut off from this circuit, and only during the T off the output voltage will appear. That means the pulse width of the output voltage will be equal to the T off interval of time. So by calculating first like the D, because like T is not known to us, and you know like T off will be equal to T minus T on, but we know like T on T will be equal to T on by D. If we will be able to calculate this D and we'll substitute here, then T on minus D on, we will be able to calculate this T off. That is what we did here, and we were able to come up after solving this. The answer is like 50 microseconds. That is the correct answer. That was like the question that was for today. Like if anyone of you have any questions regarding the understanding of these concepts or these, feel free to ask. Like if there are any questions you can ask me, because that was it for today from my side. If there are any questions you can ask, I am here to answer the questions. And if there are not any questions, then we can conclude today's meeting. Any questions? Any questions? Is anyone there? I think, am I audible now? Okay, someone is asking, could you explain the seventh question? That is fine. Like I'll come up to the seventh question. Ninth. See what is the question here. Like it is in a three-phase, three-pulse M3 type controlled converter. We have like a M3 type, that is we have a three-phase, only three devices are there. Like to have a full wave converter we need to have the 6 devices, but what is given here are only 3 devices, M3 type, that is M3 type. T1 starts to conduct at 30 degree plus some angle n degrees, and what we have to calculate is at what angles do T2 and T3 starts to conduct. Assume the conduction sequence T1, T2, T3. Coming here, you can first take a look at the circuitry. We have a balanced like three-phase system, VAN, VBN, VCN, and they are conducting, and if you can see these three devices, they are conducting in common cathode configuration. And we had seen like for this common cathode configuration, a device, if you can see like a three-phase, like this has been represented here, like this is VA, this is VA, VB, this is VA, this one, this is VB, 120 degree apart from this, like these are 120 degree phase shifted, and this is VC. And we know the device which has, if you can see this 30 degree, 150 degree and 270 degree, had there been diodes, this would have been the point of commutation, natural point of commutation at 30 degree, 150 degree and 270 degree. So at 30 degree T1 should start conducting, At 150 degree T2 would start conducting, and 270 degree this T3 should start conducting, had there been diodes, because those devices among us, these are in the common cathode configuration, which has the highest potential. If you can see at this 30 degree point, that A will be having the highest, will start to having the highest potential. So A will start conducting after this 30 degree. You got it? And it would have been up to this 150. And if you can see up to 150, like the B is now taking up. Now the B, if you can see here, that the voltage B is higher. Therefore, this T2 will start conducting. And after at 270 degree, you can see that VC is highest, and then T3 would start conducting. But these here we don't have diodes that they will start at 30 degree, 150 degree, and 270 degree. They will start conducting after we give a gate pulse to them, which is being given to some after some angle like n degree. In the question here I have represented it by alpha. So T1 had to conduct from this 30 degree, but now we are giving the pulse at alpha degree, so it starts conducting from alpha, and it will continue, like the output voltage will be like this. Now this T2 had to conduct on 150, but we haven't yet given the pulse to this. Therefore, like VA is still higher, like this is to be, this will conduct up to this 5 point. After this some alpha, like T pulse is given to the T2, like it will be a symmetric things, because there is a three-phase symmetry. Like when we will give the pulse alpha to T1, after 150 plus alpha will be giving the pulse to the T2, after that 270 plus alpha will be giving the pulse to T3. Got it? That is the answer to this question. Like T2 and T3 will start conduct after 150 degree plus some angle here, like representing alpha equal to n degree, and for the third it will be 270 degree plus n degree. Hope you understood this. Is it fine now, or some more clarification is needed? Okay. Any other questions? Like I think now it is past 9 as well. If any other questions, if you don't have any other questions, then we can conclude it for today. Are there any other questions? Okay, then this is for today, and again the first question. Okay. So the first question is about this current limit control. What is this current limit control? And this control is, we have to see like this, we are implementing the current limit control, and we have to see in which of these cases this current limit control is possible. You got it now? Firstly, like there are different loads like inductive load, capacitive load, or resistive load. We have seen, like for the current limit control we are defining a band. Like band will be Imax, some Imax, and some Imin, that will be defined. And what we'll be doing, we know when we'll be turning on this switch, the current in the inductor won't rise like abruptly, it will be with some slope. We know the VL is called L di by dt, current through the inductor won't be instantaneously. So when we turn on this switch, the current will start to rise. When the current starts to rise, it will hit the peak of the band, and we have the logic in such a way, when it hits the peak value of the band, when it is the upper value of the band, we have to turn off the device, and device will turn off. That is the current control. And then this switch will be turned off, and but the current through the inductor cannot be interrupted. It has to freewheel. It will freewheel through this diode. Then the current will start to decrease, and it will hit the lower band. When it hits the lower band, it tells it to like turn on the device. So this is the current control. So in inductive, this current control is possible. Now what will we see? We will see the resistive. So we know when this switch will be turned on, this whole voltage, input voltage, will be across this resistor, and there will be, and the magnitude of that current flowing through the resistor will be V in divided by this resistance, value of this resistance. And we know that through this resistor a constant current will flow. So here you can see we have defined the band, but if the resistive current is here, it won't hit any of the band like upper or below. So this current limit control is not possible in case of a resistive load. Similarly, if you can see a capacitor, we know that voltage through the capacitor cannot be like rise immediately, but a current can. Like if our capacitor is discharged at the instant we turn on the switch, it will like have a huge current. Instead of having some current that will rise gradually, it will have a huge current at the input, which will touch this peak of this band, and this switch will turn on, then it will turn off instantly at the start of this as well. That will be a false trigger to that. This means like that to the in case of the capacitor load, we cannot like implement this current limit control effectively. That is the only option that is like we can implement it effectively is in case of the inductive load, because like the current gradually rises to some point, and if you turn off the device, it will gradually then decrease. I hope you will have understood this. Is that fine? Is this fine? I hope you are still there. Hello? Bhaktavanchalam? Hello? Okay. So I think that is for today. Now, thank you everyone. Like, I think that is for today. Now, I think we can finish it up here and conclude session tomorrow, and we'll meet on the next Tuesday. Thank you everyone.